From the Library of Congress in Washington, D.C.
Good morning. Well, good afternoon, too. My name is Jennifer Harpster. I'm a digital reference specialist in the Science, Technology, and Business Division here at the Library of Congress. I'd like to welcome you to today's presentation, Observing the Living Oceans from Space, in which we will learn how NASA is using satellite-derived ocean-colored data sets to assess the role of the ocean in global change, and how images are used in fisheries management, agricultural assessment, and coastal monitoring. This program is a fifth in a series in 2010, presented through a partnership between NASA Goddard Space Flight Center and our division. This is the fourth year we have been partnering with Goddard. Our speaker today is NASA oceanographer, Dr. Gene Carl Feldman. Before joining Goddard in 1985, Feldman was a volunteer with the Peace Corps in Western Samoa and a fisheries biologist in Alaska, Seattle, and San Diego. He earned his Ph.D. in coastal oceanography from the State University at New York at Stony Brook. Feldman doesn't solely observe the ocean from space. He also gets his hands wet here on Earth. He has experienced an all-day dive to the bottom of the sea on the Navy's nuclear research submarine NR-1. In addition, he spent 2 weeks on board the wooden tall ship HMS Rose, swabbing decks, washing dishes, furling sails, and shortly after this trip, the HMS Rose was refitted to become the HMS Surprise, which appeared in the 2003 Russell Crowe film Master and Commander. His knowledge about the ocean is widely respected. He has authored and co-authored numerous publications and contributed to educational programs for the Jason Project, Discovery Channel, National Geographic Society, PBS, Smithsonian, and now the Library of Congress. So please join me in welcoming Dr. Gene Carl Feldman.
There's no way I can live up to that. Thank you. Thank you all for coming. I appreciate it. And oh, good, you finished. Okay, I was getting hungry. Okay, I'd like to first dispel one curiosity. I'm an oceanographer. I'm actually a fisheries biologist, but I work for NASA, which in most people's minds makes no sense. I mean, why would NASA employ an oceanographer? And hopefully by the end of this talk, you'll understand why. And you'll understand that it's actually a fun job to have. I also want to get up on my soapbox first before I get into it. The media has turned the term global change into a negative, a horrible, demonic, and that's wrong, okay? Ever since the Earth started, the Earth has changed. It will always change. That is a given, okay? There's no debate about the fact that the Earth is changing, and anyone that says otherwise is wrong. I believe that there's also enough consensus that we as humans actually are in a position technologically and by our very numbers of people here, have the ability to impact the Earth's environment on a global scale, okay? I believe that people also now agree to that. So those are two important things to understand. This is not going to be a Greenpeace lectures, save the Earth and gloom and doom. It's not. But the reality is the Earth is changing. The Earth will always change. And the important thing is for us to understand what does that change have to do for the Earth's ability to support life as we know it now, okay? We don't want to live the way the Earth was 18,000, 200,000 years ago. We want to preserve the standard of living that we have now. And that's what all the debate is about. Whether we can do that, that's another story. But anyway, okay. So I've given the library a copy of the presentation and some of the animations, so I assume it'll be available on the website, but it's also available on an FTP site that I put up. And also there's an online lecture that I put together for National Geographic a few years ago that's really good for teachers to use in their classroom. It's very, very easy to understand, a lot of pictures, and a lot of really easy to take away points about some of the things I'm going to be talking about. Okay, a number of years ago, I gave a lecture to the Utah State Teachers Association on oceanography. And someone told me, you really better figure out a way to connect with these teachers in Utah because most of them have never seen the ocean. So, now, before I get to that, I want you to take away 3 points from my talk, okay? The first one is if we care about global change or we want to understand global change, we need to understand about the oceans. It's my personal belief, being an oceanographer, that the oceans are probably the most critical component in the global cycle, in the Earth system, and probably will have the most impact on determining what will happen in the future. The second one is my personal bias. I think phytoplankton, which I'll talk about a little bit later, are probably the critical species on Earth that will determine what will happen in the future for the Earth's habitability. And then finally, why should NASA care? NASA, they throw people up into space, they send rockets and little ROVs to other planets. Why should they study the Earth? What's the deal? Anyway, getting back to my story about the Utah teachers. So what I did before I went out there, I rummaged through a bunch of photo albums that I had and figured I'd tell them a little bit of why I got into oceanography, why I cared about the ocean, how this sort of happened. So, in going through all the pictures, there seemed to be a common theme that recurred time and time again. From the time I was actually even smaller than the little picture, I always had some kind of sea creature in my hands. So from a very early age, probably starting with my grandfather on the beach at Rockaway, when he'd go out surf fishing at 4:30 in the morning, I've always been fascinated with the ocean and what's out there. It all crystallized in my mind when I was a Peace Corps volunteer in Western Samoa, which is a group of little islands in the middle of the Pacific, okay, surrounded by a lot of ocean. I was there for 3.5 years, and my primary job was to develop fisheries, and I'd worked on sea turtle conservation and a bunch of things like that. And one of the things that we had to do was to go out in little boats like the one in the lower left there every day to catch fish to feed the sea turtles that we were raising for a conservation program. And so if you look at the middle picture, that's pretty much what it looks like. You're in the middle of the ocean that looks pretty much the same everywhere you look. There's no difference that you can see from the surface that's easily discernible. But we could always go to one place and catch fish, where if we went a few miles in one direction or the other, there'd be nothing there. So while I'm sitting out in these little dugout canoes, praying for my life half the time, that's another story, but it's a really good one. I had a lot of time to think about why is that? Why are some regions of the ocean more productive than others? And what is it about this place that is more productive than another place? And this was back in the mid to late 70s. It just so happens that in 1978, NASA launched an experimental satellite called Nimbus 7 that had an instrument on board was designed to look at ocean color from space. And the idea was if you can tell something about the color of the ocean from space, you might be able to tell something about the biological productivity of the ocean. So it was an experiment. So that brings me to the first point. Why the oceans? Why should we care about the oceans if we want to talk about global change? Isn't it all CO2 in the atmosphere? Isn't it all, the solar cycles? Isn't all that? No, it's not. Okay? For instance, the atmosphere, the entire atmosphere can hold as much heat as is contained in the upper 3 meters of the ocean. Okay? The heat capacity of the upper 3 meters of the ocean, the top 10 feet, is as great as the entire atmosphere, which means that the oceans serve as a thermostat for this planet. That's where the majority of the heat is stored and released or taken up. Okay? And the surface currents move that heat around, and the three-dimensional circulation also does it. So the oceans are one of the key factors for determining the long-term climate of the planet. Not weather necessarily, but climate. Okay, the living space. When you're all in school and you hear, the oceans are 3/4 of the Earth's surface. That's true. But if you think about where does life exist on this planet? Okay, let's think about the surface. Life exists maybe a few inches below the soil to the top of a tree. So maybe a couple hundred feet. So you've got this layer on the surface that's maybe a few hundred feet thick. In the ocean, life exists from the very, very surface down to the very bottom, which is 7.5 miles deep. Okay? One of the neatest stories that I've ever heard was back in 1960, two guys went inside of a bathysphere. How did that happen? Went inside of the Trieste bathysphere and went down to the bottom of the Mariana Trench, 7.5 miles down. Okay? They were in this titanium shell that was this thick, to keep the pressure away. It took them hours to get down there. They got down. The pressure on them was equal to 50 jumbo jets pressing. The weight was incredible. Okay, pitch black, absolute cold. Okay, they get down there, they turn on the light, they look out their little teeny window, and there's a little fish just sitting there looking back at them. Happy as could be. Okay, but the point is, so from the very bottom to the very top of the ocean, life can exist. So over 99% of the living space on this planet is in the oceans. Okay, so again, the oceans are really important as far as where do things live. The land is marginal in that way. Oxygen. Did you know that half of the oxygen you breathe comes from the microscopic plants in the ocean photosynthesizing? Bet you didn't know that. Half of the oxygen you breathe comes from the ocean. And finally, and I'm going to touch on this more, carbon. This is the key story that everyone talks about. Carbon dioxide, the carbon cycle. Over 99.9% of the organic carbon that's ever been fixed on this planet by animals and plants is buried in marine sediments. Okay, so if you want to look for long-term carbon sequestration, everyone talks about, we got to get rid of the excess carbon. Well, the oceans have been doing this for millennia, and over 99.9% of the carbon is in the ocean sediments. So again, long-term strategy for reducing carbon, the oceans have that covered. All right, so that's why the oceans are kind of important in this story. Okay, why phytoplankton? I'm going to assume that most people don't know much about phytoplankton. They're not something you meet on the street every day. Phytoplankton are these microscopic plants that grow in the ocean. Okay, most of them are single cell, teeny little things, and the word plankton is from the Greek to wander. They drift with the currents. Okay, they can't swim or anything like that. So these teeny little things. The important thing is they're like the grasses on the land. They form the base of the marine food web. Ultimately, all life in the ocean, with a few rare exceptions, depend on phytoplankton for their ultimate food source. The greatest whale, the blue whale, is only 2 steps removed from phytoplankton. It eats zooplankton, krill, who feed on the phytoplankton. Okay? So the bigger you get, actually, in the ocean, the more you actually rely on the phytoplankton because they're the biggest source of food in the ocean. But they're plants. And just like the plants in your garden, they need certain things to grow. They need water. That's not a problem in the ocean. They need light. There's plenty of light near the surface. They need carbon dioxide. There's plenty of that in the surface. And what's cool is when they photosynthesize, they take CO2 out of the water, which then forces the CO2 in the atmosphere to go back into the ocean, reducing CO2 in the atmosphere. So they need that. So there's plenty of that. And they need nutrients, okay, like fertilizer. In the oceans, most of the nutrients are in the deeper, colder waters. Okay, so any place where you can bring that deep, cold water up near the surface, you're going to stimulate phytoplankton growth. So assume something like the chem lawn truck drives up to your lawn, sprays fertilizer, your lawns turn green. Same thing in the ocean. When you have an upwelling of cold, nutrient-rich water, the phytoplankton can bloom. Because they're so tied into this physical circulation to provide nutrients, the patterns that we see globally are tied to the physical and chemical circulation processes in the ocean. So there's a direct linkage between the physics and the biology in the ocean that's very, very clear to monitor. And finally, because of their taking up of CO2 when they photosynthesize, they play a major role in the global carbon cycle. Give you some numbers. Every day, phytoplankton take up 100 million metric tons of carbon. Okay, that's a lot of carbon. What's different about phytoplankton than land plants is they turn over very quickly. When you look out springtime, okay, you plant a seed. That seed will grow and it'll take months before it reaches maturity and does whatever it's going to do. Okay? Phytoplankton do that in a day or two. They completely recycle themselves in a couple of days. So every 2 to 6 days, the entire standing stock of phytoplankton in the ocean turns over, which means that they are very, very susceptible to changes in the environment, and they can respond very quickly. So a change in the environment would dramatically impact the rate at which phytoplankton can reproduce and also the amount of phytoplankton that are available. Much more sensitive to environmental change. And as I said earlier, over 99% of all the organic carbon is in marine sediments. Okay, how do you study phytoplankton in the ocean? Okay, I'm not going to talk about the spaceborne yet, but the way you traditionally do it is you go out in a boat, you take a net, you drag it through the water, you figure out how much water you filtered, and then you collect the phytoplankton in a little jar, and you calculate how many milligrams of phytoplankton per however many cubic meters of water you've cycled. And that's how we've done it historically. I had the good fortune of going to the Galapagos last summer with the Charles Darwin Foundation, and 14 of us got on this little boat and went all around the Galapagos, and they were mostly doing dive surveys. They'd go down and they'd run transects and measure the biodiversity in different areas. They've been doing this for a few years to see how the Galapagos biofauna is changing. What I did was do plankton sampling when I was down there. So what we would do, we'd go out in this little inflatable Zodiac, 3 of us. I actually did work other than just take pictures. And on the left you see what a plankton net looks like, small one. It's kind of like a stocking, a big stocking with a little bag at the end. And we had 2 of them. One was for phytoplankton with a very fine mesh, and the other one had a thicker mesh for zooplankton, which were the little animals. And so what we would do is put both nets out behind the boat, and then we just steam very, very slowly for half an hour in one direction, because we knew how long that was, and we could then calculate how much water we filtered. And then when it was over and done with, we pulled it out of the water, looked at the little jar at the bottom, and you can see that's green. Okay, so there's a lot of phytoplankton in the water. But that's how it's traditionally done. That's the way when people go out to sea to study phytoplankton, this is how you do it. Problem is, it's a really big ocean. It's a really, really big ocean. And most of the time, the weather's really bad. Okay, in a lot of the parts of the ocean, you can't do that, particularly from a little inflatable boat. So what I've got on here is a map of the world, and all these little dots represent the entire set of measurements that we have from 2002 to the present. Okay, so over the last 8 years, these are all the measurements that we have. And you can see in the Pacific, for instance, large areas of the Pacific have never even been sampled once. Okay, so this is our traditional knowledge of the biology of the ocean. It's woefully inadequate to begin to understand how the ocean changes at the appropriate time and space scales. But the other really neat thing is that phytoplankton change the color of the water. Okay, let's talk about normal phytoplankton for a second. Phytoplankton are green because they have the chlorophyll molecule in them, just like the plants outside. You look outside, it's green. The leaves are green because they have this molecule called chlorophyll, which captures sunlight and allows photosynthesis to take place. Phytoplankton are the same thing, but they're just one cell. So here's the secret to ocean color remote sensing. Okay, the more phytoplankton in the water, the greener the water. The less phytoplankton, the bluer the water. Okay, now you're all qualified to be ocean color research scientists. That's all it is. Okay, how green is the water? But the trick is you need to have a measurement in the water at the same time in the same place of the phytoplankton to be able to correlate that with what we saw from space, to tie the two together, to calibrate that information. And I'm going to get into that in a little more detail. But there are other kinds of phytoplankton that also color the water. In this case, these things are called coccolithophores. They're these little golf ball-like things, but they're teeny. And they bloom in such numbers that they actually turn large parts of the ocean, this is the Bering Sea, turquoise. Okay? And they have huge impacts on the ecology. In this particular case, all the fish that would normally swim up the Bering Sea and swim up the rivers to spawn, when they hit these blooms, they said, whoa, I'm not going in that. And they turned around and went back out to sea and didn't breed. So when this bloom happened, the fisheries populations for the fish that would have normally come in plummeted. Okay, so, and these are huge blooms. Okay, so to summarize, ocean color depends on a couple of things. One, it depends on phytoplankton. For most of the world's oceans, I'd say 90% of the world's oceans, the color that you can see from space is directly related to the amount of phytoplankton in the water, which is good. However, there are other places like near shore or very turbulent areas where other things like sediment from the bottom, runoff from the land can muck things up. So it's a little more difficult to get quantitative estimates in those kind of areas. And once you have that information, you've now got a key indicator of ocean biology. This can help us understand productivity. It can understand, because these plankton are passive tracers, how water moves. They're good indicators of water flow. If we can distinguish sediment from phytoplankton, we have a good idea of where storm runoff is. When hurricanes come, they churn up a lot of sediment and go offshore. We can track that. And more importantly, through the process of eutrophication, where we put nutrients in the water more than the water can handle, we can assess quantitatively the impact of humans on the environment. Okay, so with that knowledge that the color of the ocean is directly related to the amount of phytoplankton, this is where NASA comes in. Okay, this is the electromagnetic spectrum in the visible range, going from blue up to red. And what's really interesting, if you look in certain parts of the spectrum, it can tell you something very specific about what's in the water. Okay, so what NASA has essentially done is design instruments that are nothing more than light meters in space. Okay, I don't know if anyone has the old-fashioned cameras or light meter where if you pointed at something bright, the needle goes up, and if you pointed at something dark, the needle goes down. Okay, that's a light meter. So what these instruments in space are essentially light meters in space that look at different parts of the spectrum. So one of the channels will look in the green. Okay, if there's a lot of plankton, that green channel will have a very high signal. If there's low plankton, it'll have high blue signal. So by building instruments with known characteristics about what the ocean does, we can actually better quantify what is actually in the water. And this is where NASA comes in. Okay? But again, you say, why NASA? Why is NASA studying the Earth? It's not their job. Actually, it is. One of NASA's goals is to understand how the Earth is changing and what the consequences are for life on the Earth. Okay, that's kind of an important thing to do. So the first thing you need to do is, how is the Earth changing? Is it changing? Is it changing from day to day, week to week, month to month, year to year, decade to decade? So the first thing you need to do is actually measure the change. Okay? So once you can actually observe and measure the change, then you need to say, okay, what's causing the change? What are the forcings behind these things that are changing? And then the third thing you need to do is, how does the Earth system respond to the changes? And I'm not going to distinguish here between the natural and human-induced changes. Okay, the Earth will respond to some change. And in our case, where we can measure phytoplankton from space, that's a response of the ocean's biology to a changing environment. Okay? So that's a really, really critical step to understand, to observe the change, understand why things are changing, and then what is the impact of that change, and quantify it. And here's where people come in. So things are going to change. We agreed to that in the beginning. What are the consequences for that change for us on this planet? Because we're just another creature that lives here. Okay? And finally, and this is the most important point, once we know all of that stuff, how do we predict this into the future? Okay? So if the Earth is going to continue to change in a way that we believe, what are the consequences of that change for us and the Earth's habitability down the road? And this is where the politicians love to throw monkey wrenches in the argument. They go, they don't know what they're talking about. And to be honest, there is some credibility to that, because this is a record of sea surface temperature over the last 1,000 years up to 2000. From 2000 on, you can see the curves diverging. Okay? Those are the various model predictions based on the best scientific evidence that's out there. Okay? So you can see that there's a huge difference in what the scientists say is going to happen. Our job at NASA is to narrow that discrepancy between what the models say and have a much more credible assessment of what the future might be. Okay. We're not advocating one versus another. It's to collect the data to verify the models. And the way you do that is you observe data over a long period of time. Okay. Go back in the past as far as you can and have all the pieces of the puzzle lined up, and then you build your model and you test it in the past and see how well you can match what actually happens. Okay, so you've got your model, you've got your observations. Do my observations match my model for a time for which we've got data? And if they do, then you've got some confidence that your prediction into the future is more credible. That's why we need to make all these observations. That's why scientists keep saying we need more information, we need more data, to narrow that uncertainty between what we know and what we predict. But but with all that said, things are different. Things are different today. This is the CO2 in the atmosphere for the last 400,000 years. All right? You can see that there are these cycles associated with ice ages. CO2 goes up, CO2 goes down. People go, this has happened in the past. Don't worry about it. Yeah, it happened in the past, but if you look at what the historical high was back then, it never went above 300 parts per million. Today, we're at 385 or something. Okay, so for the last 400,000 years, we're at record levels of CO2. That would concern me. Okay, I don't want an environment that was what we faced 400,000 years ago. It was a very different world, and I don't think there wouldn't be Starbucks in every corner. Okay, the coastlines would be very different. So things are different, and I'll just leave it at that. Okay, so getting back to my point about the ships at sea, the ocean is very big and it changes very quickly. On the right, you've got a satellite image of the island of Tasmania off the south coast of Australia. Okay, you can see it in the left-hand side. It's that little teeny place on the bottom. This is an ocean color image. Right now, what the colors mean, blue is low chlorophyll, low phytoplankton. The yellows and orange mean more phytoplankton. Okay, the only point I want you to see here is look how complicated the structures in the ocean are. It looks like marble cake. Okay? The area of this image is 1,000 kilometers by 1,000 kilometers, 1,000-kilometer box. Okay? It took the satellite 1 minute to take this measurement. Okay? That measurement is made up of 1 million individual samples. We call them pixels. So there's 1 million individual phytoplankton measurements in this 1,000 by 1,000 kilometer box. Now imagine I was back on that little dinghy, or even on a big ship, okay, steaming back and forth without stopping. And every kilometer, I would take a sample, phytoplankton sample. I wouldn't stop. I'd just keep going back and forth, and I'd just do this grid. Okay? Any idea how long it might take to take the same number of measurements?
A million years.
No, but good idea. It would take 10 years, okay? It would take 10 years of nonstop sampling to take what this one satellite did in 1 minute, okay? And look how complicated the ocean is. That tells you why you can't do the complete story from ships. It's just too big a problem. So, with all of that background story, back in 1997, NASA came up with this program to study the oceans from space. And everything about this program has been kind of unique, even the way we launched the satellite.
That is video from the F-18 Chesapeake.
The instrument was called SeaWiFS, Sea Viewing Wide Field Sensor. It was the only instrument on board this little spacecraft. It was done in a unique way. NASA has never done anything like this before. Normally, NASA builds things, launches them themselves, and operates themselves. We didn't do it this way. We put out a proposal requesting industry to provide us data at a certain spatial and spectral resolution. Companies bid on it. We picked a bidder, and they did it. And the entire mission cost the taxpayer $42 million, okay? And it's now been going for 13 years. It is the best bargain that NASA has ever gotten, okay? The normal price of a satellite mission is somewhere in the $500 million range, okay? This is a factor of 10 less than that, and it's been going for 13 years. A really good bargain for the taxpayer. So for those of you who are not familiar with how satellites work, satellites in an orbit goes over the poles 14 times a day, and the Earth spins underneath it. Okay, as the Earth spins underneath it, the satellite is scanning the Earth below it. And every day, we get 14 observations like this, these orbits. Okay? And the way the orbit is designed, the next day it moves over a little bit and fills in those gaps. So every 2 days, we see every single spot on the Earth. So it's really, really, really good coverage. Okay, let me change subject very slightly. So we're making all these measurements from space, okay? I don't know if you've ever seen the way they build instruments to launch into space. You know, they've got these guys in bunny suits and super, super careful about everything they do. So this super delicate instrument. Imagine the most complicated camera you've ever imagined that costs millions and millions of dollars. Okay? And you take super care of it. And then you put it on top of a rocket. And then you explode it into space. Okay? Then you put it into an environment where every 90 minutes it goes from super hot to super cold. Because in space, when you're in the sun, it's really hot. Then 45 minutes, you're on the other side of the Earth where it's super cold. So you take this super delicate thing and you put it into an environment that is really hard. okay? So what we need to do, since the change that we're trying to detect on Earth is very small, we're looking for a very small change over a very long period of time, we have to make sure that the change that we're measuring is due to something actually changing on the Earth as opposed to the change in the instrument. Because the instrument is going to change. That's a given. So what we have to do is track how the instrument is changing in space very, very carefully. What we do with SeaWiFS, and this is the first satellite that ever did it, once a month at full moon, we flip the satellite over. We have it do a barrel roll upside down, and it takes a picture of the moon. Okay? The idea is the moon, when it's full, has a certain amount of light coming off of it. That light doesn't change. We haven't been back there mucking it up and running ROVs over it, so it shouldn't be changing much. So given that we've got a constant light source, what we do is we say this is truth, and here's what my measurement says. So that enables us to figure out how the instrument has degraded over time. And if you look at these plots, what they show is how the 8 channels that we have on the SeaWiFS instrument have changed over time. And they've changed. I mean, the red band has changed 15 to 20%. But that's okay, because we've been able to track it very, very carefully, and we can now model this change out. So we can put this correction back into the data, so now we feel very comfortable that the measurements that we're making and any change that we see on the Earth is due to that actual change rather than the instrument. Many other satellite programs, particularly foreign ones, don't put this level of rigor into the analysis. So you have to be really careful about how credible the data is compared to the conclusions you're drawing. Okay. All you need to know here that it's not easy to go from what the satellite sees to these pretty pictures. There's a lot of computer work, there's a lot of science, there's a lot of math, which I hate in there. But basically what happens is light comes off the planet. 90% of the signal that the satellite sees is due to the atmosphere. Okay, the atmosphere is very bright compared to the ocean. So the signal coming out of the ocean is very small. What happens is the light goes in. Okay, you've got light coming down and it interacts with the clouds, hits the surface of the ocean. Some of that bounces back. Some of it actually goes into the ocean. Okay, that's the light that we're interested in. It then interacts with what's in the water, and some of that light's absorbed, some of it's scattered, and some of it is reflected back out of the ocean. That light that comes back out of the ocean has now interacted with what's in there, and its color has changed. Okay, so that signal coming back out of the ocean, going back through the atmosphere, through all the clouds and all that stuff, is what we see in space. That's what we're trying to understand. Okay, and that's that first step where we take what the satellite saw, get rid of the atmosphere, and then we have something about the color of the water. Okay, then what happens, once we now have that measurement of the color of the water, we then have whatever those ships told us about, here's the color versus the amount of phytoplankton. That gives us an algorithm that can relate the two. So that's what we do it. And then we map it and we make these pretty pictures. And when we're all said and done, this is what we come up with. This is a SeaWiFS image off the coast of Florida showing the Gulf Stream. And they're not just pretty pictures. They're actually quantifiable information about the amount of chlorophyll A, which is that molecule in phytoplankton in the ocean. The color bar is along the top. So what you can see is out in the deeper parts of the water where there's less nutrients, the ocean is less rich in phytoplankton. As you get near the shore, where you've got mixing processes that are bringing the nutrients up near the surface, you've got more productivity going on. So it goes into the yellows and to the reds. I wish I could point, but I can't. If you look off the coast, you'll see these circle-like features. Okay, this is the impact of the Gulf Stream on the shelf, creating these eddies, and these eddies form little oases of life because they're nutrient-rich, they're self-contained, they allow little ecosystems to develop. So they're really interesting. Our friends at NOAA use this data in a real-time way. They get this data, and not all phytoplankton are good. Some phytoplankton actually are toxic. And if they bloom in large enough numbers, they can actually hurt people either directly or because the shellfish take them up. If we eat that shellfish, we can get sick. So they have a harmful algal bloom product that they produce using this data and their knowledge of the oceanographic conditions to warn people about beaches needing to be closed and shellfishing areas that need to be closed. So it has very practical applications. getting back to the Galapagos for a minute, the Galapagos there in black, we were in between those two islands on the left side, the one that looks like a horseshoe, a seahorse, and that little one. So we were going back and forth across there measuring phytoplankton. And you can see here on June 24th, not much going on. 2 weeks later, it bloomed. Okay? We're talking thousands of square kilometers of ocean went from essentially a desert to a rainforest condition. Okay? And then 6 days later, the bloom has subsided and it's drifted off somewhere else. So it changes very, very rapidly. And again, the thing about the ships is you can get a really good understanding of that particular place where you were, but you can't put it in context. The satellite data allows you to put these individual measurements into a much broader context, which is one of the strongest reasons why we need satellite data, to take that detailed information and expand it globally. Another thing that came out of SeaWiFS, which we hadn't even thought of, which was kind of interesting, had to do with coral reefs. Everyone knows the coral reefs are endangered. That's, again, not a problem, not a question. It's a problem. There's a group called the World Climate Monitoring Center that has this thing called Reef Base, which is a map of all the reefs around the world. And they've digitized this map, and they use that to track the status of reefs. So every year they put out this assessment of the world's coral reefs based on this map that they have. Well, when we started processing the SeaWiFS data and we started comparing the location of the reefs that we were seeing in the data versus where the reef-based maps were, we saw that there was a problem. So what we ended up doing was coming up with a partnership with this group to essentially correct the locations of a lot of their reefs. This is a reef off of Belize. And in this particular case, the reef was 50 kilometers off from where they thought it was. So it's that old Joni Mitchell song, you don't know what you got till it's gone, or, okay? If you don't even know that there's a reef there, how are you going to be able to assess whether it's in danger or okay? So we corrected almost 1,800 reefs based on just this project, which is really kind of cool. So we've updated Reef Base, and now they're in a better position to actually accurately monitor the reefs. Okay, another thing that we've done is actually try to use the satellite data to do something closer to home in the Chesapeake. Chesapeake has a problem, too many nutrients going into it. I don't need to get into the details again. Nutrients normally are okay, but when you put too many of them in a closed system, you've got something called eutrophication, which is too much nutrients for the system to absorb. And what happens is phytoplankton bloom, because they're, just like the ChemLawn guy comes in, they die, they sink to the bottom, they decompose, the oxygen gets depleted in the water, dead zones, bad stuff. In addition to that, the increase in phytoplankton decreases the clarity of the water. It becomes murky. Because of that, the seagrass beds in the Chesapeake have almost vanished in many places. Okay? Seagrasses are really, really important for habitats for larval fishes. They stabilize the bottom. They absorb harmful toxic things. So seagrasses are really good. So it's a bad situation. The various states around the bay are trying to monitor the bay, try to understand it. But again, what they're doing is they're doing it the traditional way. They go out every month and they take these samples in these locations. Okay? So what we've done is partner with them to provide daily observations from space of the Chesapeake Bay that can be merged with the in situ data. Okay? A few years from now, there's going to be laws, I can't remember the exact terminology, that will actually have penalties for excess nutrients, the health of the bay. If the bay isn't improving using certain metrics, there will actually be penalties on the industries and developers that are doing stuff. So again, what we're trying to do is give a better sense of the spatial and temporal scale of the change rather than just these few points. So we're trying to figure out how to put the two together. And this long-term plot here, the little dots are the measurements from the ships. The blue line is the SeaWiFS record over the last 10 years. The red line is another satellite called Aqua that has a similar instrument on board, and you can see that they're very similar. So what we're able to do now is feel fairly comfortable that the measurements that we're getting from space are at least as good and probably better than what we're actually getting from the ships, more so because they have that spatial coverage. And I'm not going to deal with that one. Okay, let's get global. SeaWiFS was launched in August of 1997. Started collecting data in September of 1997. You probably don't remember, but that was the El Nino of the century. Started then. Okay? So here we had this record of one of the most anomalous conditions in the ocean ever. But we had no idea what normal was. So we started collecting data, and then starting in May of 1998, El Nino collapsed, and something called La Nina kicked in, which is essentially the reverse. Winds started blowing, the upwelling came back, and the oceans bloomed. And what you can see, look at the equator, okay? Equator is sort of in the center of the image. On the top one, it's just blue, right? If you look at the bottom image in July of 1998, you've got this, in my screen, it's more yellow than green. It's probably hard to see up there. But what happened was the entire equatorial Pacific went from almost no chlorophyll to bloom conditions in the course of about a month, okay? So what this says to me is that the natural system can respond to change. It's evolved to respond to change. El Nino is sort of like a massive dose of global change in 9 months. Okay? It's what we're talking about in the long term. But the ocean's adapted to that. And the life in the ocean that responds to this has figured out evolutionary strategies to deal with this. Now, I don't have time to get into the details, but it's a fascinating story as to how we can use El Nino as a surrogate for global change to understand the temporal scales involved with how systems can respond. It's a really neat story. Okay, I've been talking a lot of pictures and all of this stuff. Let me throw some numbers at you, okay? If we take all the plants on the land and all the plants in the ocean, and we say how much carbon do these things actually take up out of the atmosphere every year, it's 110 billion metric tons per year of carbon taken up by the plants. To put that into some kind of thing you can grasp, imagine a train of coal cars. Okay, coal is essentially pure carbon. Okay, so let's build a train, fill it with coal, and now let's take that train back and forth to the moon 45 times. That's how much carbon the plants take up every single year. That's a lot of carbon. Okay, most of that is recycled. Particularly on land, if you think about it for a second. This is when people talk about, oh, we have to plant trees to prevent global warming. Pardon me, but that's not the answer. It's nice to look at, and it's a good short-term solution, but think about it. You plant a tree, it grows. It takes up carbon while it's alive. It's going to last 100, 200 years maybe, okay? Then it dies, it falls down, decomposes, CO2 goes back into the atmosphere. Every year, the leaves drop. That's all the carbon that's been taken up by that tree every single year. Okay, we're not surrounded by leaves. Those leaves decompose, and all that CO2 is back in the atmosphere. So carbon sequestration on land is just a short-term thing. It's not the long-term solution. In the ocean, a lot of the carbon is recycled, but a small rain of that carbon goes down to the bottom every year and gets buried in the sediments. And as I said, over 99% of the carbon is in the marine sediment. So that's where we want to look for the long-term solution. So one of the things that I'm going to skip this one. Okay. No, I'm not. It's cool. But the problem is I'm going to go over here, okay? What this shows is the last 1,000, okay, I'm going to go over to this monitor over here, because I need to use my finger. This will show the carbon dioxide in the atmosphere over the last 1,000 years, okay? So, watch. Okay, so here it is over the last 1,000 years. And you can see it's gone up a lot in the last 100 years. Now, if we look at the last 50 years, we see there's a cycle. Up, down, up, down, up, down, up, down, up, down. Now we're going to look at 3 years. Up, down, up, down. Watch what happens. I'm just going to call it out. Winter, summer. Winter, summer. Winter, summer. Back to winter. Okay? What's happening here is that as the plants grow in the northern hemisphere winter, in the northern hemisphere summer, they draw CO2 out of the atmosphere. So the CO2 in the atmosphere goes down every single summer because CO2 is taken out of the atmosphere. But then in the wintertime, all that stuff is respired back into the atmosphere. It goes back up. So this is SeaWiFS data of land and ocean. what it showed us for the first time is that close coupling between this biological process, you can actually watch it, and the CO2 in the atmosphere. But what you also see is that it never comes back to the same place after each year. So we were all kind of thrilled with this. We said, wow, this is really cool stuff. And so we did a more detailed assessment, and we actually calculated the amount of carbon taken up by both land and ocean for the first 3 years of the SeaWiFS mission. Okay, so if you look at the top, just look at the light colored line, the open diamonds. Okay, you can see that for the ocean, over that 3-year period, phytoplankton productivity went up for those 3 years. Okay, the land, on the other hand, had this big seasonal cycle, but it was flat. So something happened over those 3 years that the ocean responded to that did not impact the land. And we thought this was really great. We wrote a paper, got the cover of Science, the copies of it over there, maybe they're gone. So this was cool, right? Everyone thought we were great. We got on the news, fantastic stuff. Sensor didn't die, it kept collecting data. And turns out that after that 3-year period, we had a reverse trend, okay? Started going down. This is ocean productivity from the beginning of the SeaWiFS record to 2006 when this next paper was written. So we said, okay, what happened? Well, what happened was that first piece was an anomalous condition. That was the El Nino La Nina period where the oceans essentially just bloomed like crazy. And because the area that is attributed to El Nino and La Nina is so huge, it had a huge signal on the global change, on the global cycle. To better explain that, 2 pictures. The top one is change in sea surface temperature. All you need to look at is that big area in the Pacific that's red on the top. Okay? What that says is over that same period from 1997 to 2006, that area in the Pacific and other areas as well was much warmer than usual. Okay? Because we have coincident records of sea surface temperature. Okay? If you look at the bottom image, you'll see that there's a corresponding region in the Central Pacific and other places where there's also red, where there's lower productivity. Okay? This is the first time where we've had the global data set to be able to link changes in long-term productivity in the ocean and changes in the environment. And what this is related to, and it's kind of interesting because it does have an impact on the long-term story, we came up with the mechanism for how the phytoplankton in the ocean may respond to a changing climate. Okay? Remember I said that for most of the ocean, the nutrients are in the deeper, colder waters? Okay. That big area in red is an area that's pretty permanently stratified, which means if you ever dove in a lake and you go down and it's nice and warm on the surface and then you hit this layer and it's cold, okay, that's called a thermocline. You get very little mixing between those 2 layers. So what happened in these big red areas, you've got all this nutrient-rich water down deep, but it's separated from the top by this thermocline. And if you warm the top even more, it makes that barrier even more impervious, which means that the warmer the ocean is in certain places, the less nutrients you're going to be able to get up in there. And that bears out here in the fact that those areas that were warmer, that are generally stratified, had much less productivity. So it now demonstrates a mechanism for how the ocean's biology is going to change. And what we did, we came up with this thing called the climate index, which was an indicator of using winds and temperature and cloudiness of how stratified the water would be. And what we did was superimpose the change in productivity with this climate index, and they laid right on top of each other. So why this is important is if we look at the models that people are giving us, and they predict changes in the ocean temperature, we can now go back and use this information to predict how the phytoplankton may respond to that, and then based on that, how the zooplankton and how the fisheries may respond. So there may be areas that in a warming ocean will have a very, very different environment for the biology than we currently have now. And I'm going to leave you with this one. This is 10 years of SeaWiFS data of land and ocean. We call this a global biosphere. And what this does for me, NASA studies all these other planets, and they all have atmospheres, and they all have geology, and they all have chemistry, and they all have physics. But as far as we know, there's no other planet where the combination of all of those factors have combined to produce a place that can support life. And this is life on this planet. This is a living planet. Okay, you're literally watching it breathe with the seasons. It changes from year to year. And this is what we sort of have to take care of, because we don't know that there's another one out there like this. And I'll just let you look at that, and I'll open it up for questions if you want.
I like that. Watch it breathe.
That's what it does.
So we do have questions. Yes.
I wonder if your data can or has tried to separate out the effect of the increased technology as all of these measurements have developed, both in the past and then on the extrapolation out into the future. None of the studies I've seen have taken technology into consideration, and if you don't, it seems to me that you have eliminated a major measurement piece from the statistics.
You mean whether or not we can rely on technology to get us out of the mess?
That and what differences in technology have gotten us into the mess, both.
Well, that's pretty clear. I mean, if you look at the CO2 record, it directly relates to the Industrial Revolution. Okay, when we started burning fossil fuels for industry, way before cars, okay, back when the coal plants and all of that, and we started burning oil, the Industrial Revolution is when the curve went crazy. So there's a direct correlation between industry burning fossil fuels, which had never happened before other than people burning fires. I mean, you think about prior to the Industrial Revolution, the only CO2 emissions to the atmosphere was some bunch of people sitting around a campfire cooking food.
Okay, so you have a subjective conclusion as opposed to a scientific.
No, there are people that actually measure carbon inputs from the various industrial sectors. So there are people that do that. I don't do that. I'm an oceanographer. But there are people that actually look at every single contribution of carbon to the atmosphere from the past to the present, and then how that's going to change in the future, using various strategies like, okay, if we reduce fossil fuels and we have electricity generated from nuclear, what's that going to do to the equation? If we go solar, what's that going to do? There are people that study that. So, and that's what a lot of those projections to the future are based on. If you change things this way, this is the impact it's going to have. If you don't do anything, this is what's going to happen. So there are people that do that. I don't have that information.
Thank you.
Yeah.
Guess I'll come back over here. Oh, that's you.
Yeah. This is slightly tangential, so you can choose to address it or not. I was wondering if you could address sort of the current state of discussion about using phytoplankton as a geoengineering tool for increasing carbon sequestration.
Yeah, there's an interesting story about that. I think it's a stupid idea. I think.
I'm not attached.
Did I really say that? Okay, let me tell you a little backstory. I was at a meeting when I first started doing this ocean color stuff. My dissertation was on the Galapagos. And I had this beautiful image of the Galapagos and this plume of plankton downstream of the Galapagos. And I was at this meeting in California with this guy named John Martin from Moss Landing Marine Lab. And so we were sitting around having beverages, and he looked at the picture, and I explained what it was. And he started thinking, he said, wow, there's like no nutrients down there, but there's volcanic soil coming off the Galapagos that have iron, a lot of iron-rich sediment. And you've got this downstream plume from the Galapagos in an area that is normally rich with nutrients. Why is it only where you've got the sediment? And he came up with the iron hypothesis. And based on that image and John's iron hypothesis, they went out and actually tested it. South of the Galapagos, they went out with a ship full of iron, fertilized the ocean, and lo and behold, it stimulated phytoplankton growth. They did subsequent ones down in the Antarctic. Again, they're looking for high nutrient, low iron environments. And so the idea is if you can fertilize the ocean with iron in places where there's a lot of nutrients, you're going to get phytoplankton to grow. They're going to take CO2 out of the water, which will then draw CO2 out of the atmosphere to replace it. Some of those guys will die and go to the bottom, and you'll sequester phytoplankton, sequester carbon. In theory, it's good. If you look at the long-term, the large energy balance, it probably takes much more energy to produce the iron that would be, and then take it in a ship all the way down there for the amount of carbon you're actually going to sequester. It's one of these things where the math just doesn't work out. So, plus, you're potentially seriously impacting an ecosystem that you have no idea what the effect is going to be. So I would not want to genetically alter the planet with these kind of experiments. It could really damage things. Because you might stimulate the wrong kind of phytoplankton. So let's say you've got an ecosystem that's built up with eating very, very small phytoplankton, the little guys. And all of a sudden you go down there, you dump all the nutrients in there, and now you've selectively favored the big ones, the big diatoms. So now you've got all these big diatoms, but you've got a whole ecosystem based on little guys. Ecosystem collapses. Penguins die. People are not happy. So.
Yes. Why are there more nutrients in cold water than in warm water?
It's not just temperature. It's location, location, location. Okay. The oceans mix very slowly. Okay, thousands and thousands of years. So you've got this huge pool of nutrients that once they get below the surface in the deeper waters, there's nothing that will take them out. The only thing that takes the nutrients out of the water are phytoplankton photosynthesizing. So once the water gets below the surface, those nutrients will be there forever. Okay? So when they come up to the surface, they'll generally warm up, and then the phytoplankton can grow. And so it's not warm water has less nutrients than cold water. It's just that where that water is. So the deeper, colder water generally has this pool of nutrients. You've actually got more nutrients near the shore where you've got runoff and things like that, which is very warm. Okay?
Wondering about using the light sensing technology to measure other types of change over time in terms of light coming off of this. So for instance, are we interested in change over time in infrared from the surface of the Earth related to global change?
There are instruments measuring the complete spectrum from space. In fact, one of the programs that I'm working on right now, it's called Aquarius, and it's using microwave sensing to look at the ocean. And if you know the emissivity of the ocean in a certain L-band of microwave plus the temperature really, really precisely, you can determine salinity. So the goal is to measure global salinity every day, which is really important. There's surface circulation of the ocean, which is really important. But even more important for the long-term climate is the three-dimensional circulation, where you've got this cold water forming up north, sinking, taking heat with it. So in order to understand the three-dimensional circulation, we need to understand the ocean's density. So temperature and salinity are the two determinants for density. We understand temperature really well. We can measure that from space. We don't have salinity measurements. So if we can measure salinity and temperature, we can then have a three-dimensional, a global picture of surface density, which using the models will tell us how the three-dimensional circulation will go. And again, with that, we can then test the models to see whether the circulation models are working. But yeah, there are people that use infrared to study vegetation on land. It's a really good signature of vegetation using the infrared wavelengths on land. Landsat has infrared bands that they use for that. So yeah, again, the information coming off the Earth across the spectrum can tell us stuff. And different disciplines carve up their part of the spectrum based on what they want to understand. So it's kind of cool.
Where did you get your data for the 1,000-year carbon scale?
A lot of those are from ice cores, and particularly the Vostok ice cores, and I think they do tree ring analysis, but I think most of it is snow and ice cores. Again, it came from NCAR. I mean, that's who I got it from, but I think they used ice core data to get that. The little bubbles are trapped in there in the ice, and they can sample that and measure the CO2 in the bubble.
So that's what they use for the 1,000-year?
Going back to the 400,000.
The modern.
Modern is, there's an observatory in Hawaii called Mauna Loa that was built by this guy, Dave Keeling, back in the 50s. And he's kept a record every day of Northern Hemisphere CO2 in the atmosphere. So that detailed record that we have of the ups and downs only started, I think it was 1952, I don't remember, from Dave Keeling in Hawaii up into Mauna Loa Observatory.
Is there any evidence that climate change is causing changes in ocean currents, or that currents themselves might be able to combat or fight against climate change?
There's no evidence now that the currents have changed. There are predictions, depending on what may happen, that currents could change. Surface circulation is driven mostly by winds and temperature. So, yeah. If the circulation does change, the climate will change dramatically. I mean, if you look at vegetation types and temperature across a given latitude, say the Atlantic, okay, from here, if you go across the Atlantic from, say, the East Coast over to the west, okay, I was in Ireland two years ago. They've got palm trees in Ireland, okay, and that's as north as Nova Scotia. Okay, that's because the Gulf Stream brings this warm water over to Europe. So the Gulf Stream takes the heat that's trapped on the Earth's surface in the equator and pumps it up through the Atlantic and warms Western Europe. So yeah, circulation would greatly affect the climate of regions and make them more or less habitable. Some places might be nice, be better. Some places would probably be worse. You don't know.
Hi, I just want to leave you with two pieces of information, particularly for classroom teachers. I'd like to give you my contact information. I'm Jeannie Allen. I work at NASA Goddard Space Flight Center, which is NASA's lead Earth observing center, supporting teachers and museum educators. My email address is jeanette.e.allen@nasa.gov. It's Jeanette with 2 N's and 2 T's. And the other piece of information is that there's an online journal called Earth Observatory, which is it's written at about a high school level, and it covers all of NASA's Earth observing, and the kind of question you asked could be answered there. The URL for that is also pretty simple. There are no W's. It's just http://earthobservatory.nasa.gov.
And if you want to get in touch, we can.
You can always
put you.
get that through the library.
We could be able to. Thank
Mm-hmm.
you.
Thank you very much.
This has been a presentation of the Library of Congress. Visit us at loc.gov.